Okay, so what I would like to do first is to summarize a few lessons, general lessons that we learned from the general discussion of dimensionality reduction and encoding from n inputs to m outputs. And I'll try to emphasize first some of the lessons which are really very general. So the first one is that we saw that since this transformation inherently involves a dimensionality reduction, the first question that one should ask is, what is the subspace? How is the subspace, the full space of n inputs reduced into a space of lower dimensionality of m outputs? And the answer that we found is that from the principles of maximization of information, the best choice is to end our additional assumptions about noise. The best choice is to choose only the m components, principal components, with the largest variance. What we call the first m principal components, because we always the convention is to order the principal components according to decrease of variance. So this is one important lesson. And in principle, for a sensory system, this is a prediction. For example, it tells us that we expect the outputs to be completely oblivious to any excitation of the inputs along the dimensions of the m+1 to n directions, right? Okay. The other very general conclusion that we obtained is that with increase of input noise, what we find is that it's beneficial to shift resources towards the components with the larger variance. So if with a case of very low input noise, we actually devoted more resources, in a sense, to the components with small variance. In the case of high input noise, we devote more resources to the components with low variance. And it makes sense because these are the components that contain information once corrupted by the input noise. These are the components that contain information about the true input, about x, whereas the components with low variance of x are very much corrupted by the noise, so it's not beneficial to encode them. So I'll write this: resources shifted, shift towards components with large variance, with large lambda or large variance, input variance. This, of course, is also a prediction. It tells us that if we look at perception, we expect that as we increase the input noise, if the sensory encoding system adapts to the statistics of the noise, if it is able to do so, and for any statistics of the noise, for any variance of the input noise, choose an encoding scheme, an encoding strategy which is optimal in the sense that we discussed in the past 2-3 weeks, if the sensory system is able to do so, we expect to see a change in the thresholds for perception of different components of the input in such a way that when we increase the input noise, we will see that if perhaps, for example, if there is very high input noise, we expect our sensory system to have lower thresholds, better discrimination for the high variance components, for the low variance components, but when we go to high input noise, we expect it to have more sensitivity to the low input components. And again, you can relate this already to the plots that I showed you from the paper Attic and Redlich, and they showed some data from psychophysical experiments that were done by Van Ness, and you saw that something like this is happening in the retina, which tells us a very interesting and deep thing about the retina. It tells us that the retina does not use the same encoding scheme all the time. It adapts to the structure, to the type of inputs that it gets. It somehow senses whether there is low input noise or high input noise and changes the way in which it encodes the stimulus. And finally, for the specific situation where we have a constraint on the sum of the variances of the output units, we have a very detailed theory that tells us what we expect for the encoding of each principal component, a very quantitative and detailed theory for the alpha i's. We have an expression for them. So before we continue, I'd like to discuss what are some of the conclusions that we reached which are less general and in a sense therefore point to some weaknesses of the theory. Okay, so one weakness, yes? Where? Detailed theory for the alpha i's. So one weakness of the theory is that it actually does not predict for us what is the structure of the receptive field. Because as I remind you, we saw the structure of the receptive field. There are many, many different solutions which all have the same mutual information between the output and the input. We saw that we can take W. So let me just write this down. Many possible solutions for receptive fields. And as we saw, we can take W and transpose and multiply it by any orthogonal transformation. And we will get the same mutual information. So we cannot predict, based on what we've discussed so far, what will be the very specific structure of the receptive field. Another weakness of the theory, which is less obvious, but I already mentioned it a few times and I'll do it again, is if we go to the detailed theory that we got, the detailed expressions for the alpha I, and this has to do with the constraint. We assume the constraint of the form sum over yi square is equal to some mq, right? This tells us something about this assumes something about the constraints that are facing, that the biological system is facing. Now, it seems very reasonable that there is some constraint about the output of the output units, the variance of the output units. Maybe because there's some energy cost for spiking, so we want our ganglion cells not to spike too much. Maybe because of some other constraint. But it's not clear that when we have to decide how to shift resources from one ganglion cell, say, to another, or from one output unit to another, this constraint enters as a sum of the variances. Maybe it enters as a sum of the square root of the variances. Maybe that's the form of the constraints that we should choose. Maybe it's a sum over the log of the variances that we should constrain. This is very unclear. We don't really have an understanding which one of these constraints we should choose. And I will tell you that suppose that we take one of these other constraints and repeat everything that we've done so far, what we would find, first of all, that we have a little bit of a problem because, things become a little bit more complicated because this constraint is invariant to a unitary transformation. These constraints are not invariant to a unitary transformation. Okay? But let's suppose that we choose what I call the WPC solution, meaning that we take the eigenvectors of the covariance matrix of the input, we project on them, and we encode each one of the coefficients separately in one of the output units. So this is, I claim that even for this solution, even for the PC solution, which is well defined for each one of these choices of constraints, we will get a different prediction for the detailed forms for the alpha i's. How they depend on all the parameters, right? The alpha i's, how they depend on all the parameters, which are the lambda i's, delta, epsilon, and q. So the next thing that, and I want to again mention, to say again that these different predictions for the alpha i's has to do with the fact that we need to allocate our resources, encoding resources between the different output units, and these different constraints will have different implications for what is the best way to do this. So the next thing that I want to do is to discuss encoding of visual stimuli in the retina. And the reason is that in the retina, as you will see, we'll have additional constraints, biological constraints on the structure of the receptive fields. We know that these exist. And I will try to convince you that under these constraints, both of these problems are alleviated. We can really come up with a very detailed predictions for the alpha i's, for the structure of the receptive fields. And this is really one of the most successful computational quantitative theories that have been proposed in neuroscience. So I'm discussing now visual encoding in the retina, and I didn't yet mention what I will change, but I will argue that there are additional constraints. We know something about the structure of the receptive field, and under that, which is very general, I will explain in a moment what it is. No, the structure of the receptive fields. Okay, the input, it's also true that we know something about the statistics of visual stimuli, which I will discuss in a moment. But we also know something, you know what, let me say this already now. So let's think for a moment. Suppose that the retina would adopt the WPC solution. What would the receptive fields look like of a given ganglion cell? So remember, what does the WPC solution mean? So suppose that the retina would adopt what I call the WPC solution for the encoding of the stimulus. My question is, what would the receptive fields look like? So I remind you, the WPC solution means that you project into each one of the eigenvectors of the input, and then you encode the coefficient in one output cell, another coefficient in the next output cell, and so on. So what would the receptive fields look like? So we need first to say what are the eigenvectors of visual stimuli, right? Because we know that in any case, we're going to project on them. So does anybody know what are the eigenvectors of visual stimuli? Okay, I will give you some hints, and let's see if we reach the conclusion. We know that visual stimuli are invariant to translations. So, I mean, in the statistics, okay, good. If I look at the visual stimulus from here and I shift my head to the right, it will have the same statistics. Now, you've been discussing in the TA sessions, the last TA sessions, eigenvalues of matrices that have translational symmetry, and what were they? Fourier modes, right? So this is a very general statement. I mean, actually, if you ask yourselves, why are Fourier modes and Fourier analysis, why is it so important? Why do you keep learning about it in various courses? The reason is that Fourier modes are always the eigenvectors of any matrix that has translational symmetry, of any operator matrix that has translational symmetry. So we know that the eigenvectors of the stimulus are Fourier modes. So if we adopt the WPC solution, what would the receptive fields look like? So receptive field, remember, that's in our model it's the double, it's a row of the W transpose. But it tells us really how a given output unit sums up the inputs from the world in order to decide what its output is going to be. So if I'm telling you that we're in the WPC solution, each output unit is encoding the coefficient of one of the Fourier modes. So what will be the structure of the receptive field, the spatial structure of the receptive field? It will be like a Fourier transform, right? It will be one. So each receptive field, if I want to project, if I want to extract from the input stimulus a Fourier mode with this periodicity, I multiply the inputs by this function, right? This is how we extract from a function a Fourier mode. We multiply it by the exponent of e to the ikx, right? We sum over x. If this is the input, s of x, something like this. So the structure, if the retina would adopt what we call the WPC solution, the receptive fields would be Fourier modes. If I would test what is the receptive field of a particular ganglion cell, I would see that the stimulus that excites it, what it's sensitive to, is a projection of the whole visual scene over a particular Fourier mode. And this is very far from what we know about receptive fields in the retina, right? Receptive fields in the retina have a very different structure. They're all localized. For each ganglion cell, the receptive field doesn't look like an infinite Fourier mode. It looks like some Mexican hat, and it's localized. And if we look at another ganglion cell, we find the same structure of receptive field, but only with a shift. And if we look at a third ganglion cell, we'll find again the same structure of receptive field with another shift. So the constraint that the receptive fields of ganglion cells are localized and they are all translated versions of each other is something that we want to incorporate into our theory. And I claim that once we do that, we will have, under this assumption, we will have a precise prediction for the receptive fields. And you will see that there is no question of how to distribute resources between the output units, which we had in our general theory. And the reason is that essentially, once we assume this symmetry, all the ganglion cells will have the same variance. You cannot escape this conclusion if you assume that the inputs have translational invariance and all the receptive fields are translated versions of each other. So all the ganglion cells will necessarily have the same variance. Okay. Yes, that's what it means, and you now may start to understand why in the last TA session you discussed a very particular form of matrices. We will see this in a few minutes. So this is an introduction to what we're going to do. And now I'm really starting to talk about encoding of visual stimuli. And let me mention first that to make life easy for us, I'm going to only consider the spatial aspects of the encoding. I'm not going to consider the temporal aspects. We know that images in the world have correlations both in space and correlations in time. Many of the ideas that I will talk about relating to space are also relevant for encoding in time, but I will not do this explicitly in this course. So when we start to talk about encoding of visual stimuli, the first thing that we need to discuss is the statistics of images. Which images? We will describe some vague notion of natural images. It's very clear that if you take a snapshot of an image in the natural world or even in our world, they will have very, very different statistics from just a set of random pixels, right? And it turns out that there are some very general, very robust properties that one observes if one looks at the statistics of images of this type, images from the real world. So I'm starting to talk about the structure of the inputs now, and putting this in another phrasing. I'm going to talk now about the statistics of natural stimuli. I won't tell you a lot about it. If you're curious to read more, there are some papers in the Moodle. But I will just tell you a few basic facts. So first of all, when we want to characterize the statistics of natural images, the first thing that we must do in order to get some sensible results is to normalize the intensities by the average intensity in the image. And the reason is that really lies in the physics of what is sensory perception of images. Sensory perception of images is the reflection of light from objects in the world, but the intensity of light can change drastically under different conditions. So if we will not normalize by the average intensity, we will get extremely wide distributions of intensity, which just comes from the fact that sometimes we're looking at an image in daylight and sometimes we're looking at the same image at dusk and so on. So the first thing that we're going to do is always take the intensities and generate from them some normalized variables. Let's call them S of x. X is the position in space. And let's call I of x the intensity that falls on our sensors. And we'll just divide it by the average intensity. Or sometimes people look at the log of this quantity. So for this quantity, it's more or less has zero mean, because for the mean intensity this is zero. Not precisely, but more or less. And for this we might want also to subtract 1 so that we will get a number which is negative or positive. Okay, and now let's ask some questions about the statistics of this S. Okay, so the most basic property that has arisen in our theoretical discussions is the correlation function, right? So I'll continue here. So I is the intensity of the light, or the intensity of the activation of our photoreceptors or our sensors if we have a camera. And I will just divide this by the average. So S is just a variable that is a normalized version of the image. Okay. Say average over the whole image. So we assume that the whole image is large enough that we can extract from it very reliably something that tells us about that allows us to divide by the normalization that comes from the change in the light that is falling on in the intensity of light in the world. And again, the problem is that if I would not do this and look directly at I, if I, for example, would look what is the variance of I at a given point, this variance will be dominated by the changes coming from changes in daylight. They will not come from the properties of the world. Okay, so let's look, for example, at correlation functions. I'll define it as follows. I'll call it G. G of x and x prime is equal to the correlation between x and S of x prime divided by S of x, S of x prime. And what do I mean by these averages? What I mean by these averages is that I will perform this average over many, many different images. Okay? So what are the properties of this correlation function? The first property is translational, very important property, is translational symmetry. Meaning that G of x prime is really just a function of x prime minus x. Consequence. What are the eigenvectors of the correlation of this if I would discretize the image, okay, and I will look for the eigenvectors of the correlation matrix, what I will find? What will I find? If I would look at it, so here I'm still writing things in terms of continuous positions in space, but suppose that I discretize the image as we do when we take a digital picture, and I will look at the correlation matrix of the image. What does a translational symmetry imply? You know the answer because we discussed it a few minutes ago. What will be the eigenvectors of the correlation matrix? Fourier modes, right? So the consequence of the translational symmetry is that if we if we Fourier transform the image, we look at SAK, that's for S of k, that's the Fourier transform of S. If I look at S of k prime, since these are the Fourier modes, the Fourier modes are the eigenvectors, different Fourier modes are uncorrelated. So I'll get something only if k is equal to k prime. Actually, it's going to be delta k is equal to minus k prime, and this has to do with the fact that the Fourier modes are complex functions. But essentially, this means that this is the same periodicity multiplied by some function of k, which in fact is the Fourier transform of this function. Okay, so in Fourier space, images are uncorrelated, different Fourier components are correlated, and there is some function that tells us what is the power in each one of the variance in each one of the Fourier modes. Now, I will also assume another symmetry, translational symmetry, that this is a function only of the difference between the positions x prime and x. I will also assume a rotational symmetry. This is not a precise statement about natural images. But I will assume it to make life more simple for us. So rotational symmetry means that G of x prime minus x is really a function only of the absolute magnitude of x prime minus x. And in Fourier space, it means that G of k is a function only of the absolute magnitude of k. Okay, so initially it was a function of two vectors, right? One x is a two-dimensional vector and x prime is a two-dimensional vector. Under the assumption of translational symmetry, it depends only on the difference of these two variables, so it can be written as a function of one vector. I'm not telling you what is this function yet. I will tell you in a moment. Yes, in principle, I could have used a different letter because this is a function of two vectors, this is a function of one vector. Just in order not to constantly define new functions, you should understand from the context whether I'm meaning this or this. Here I'm writing it as a function of just one vector, and I'm allowed to do this if I'm assuming translational symmetry. Okay? You are right that technically this is a different function than this one. This is a function of two vectors, this is a function of one vector. That's right. So it's a function of two vectors. But if there is translational symmetry in the world, it will really depend. This function will not depend. It will have a very special structure that it will depend on the difference between these two vectors. Okay? Ken? Yes? This is you're just asking what is written here? Yes, k bar plus k bar prime. Yes. Okay, so this has to do with the fact that the Fourier modes are complex functions, and what I could have written here S star of k, S of k prime, which is the proper way to do a projection when you have complex variables. You need to put a star on one of the variables. And if I would have done that, for real functions, the Fourier transform of minus k is the Fourier transform of k starred. So if I would have done that, I would get here k minus k prime. It's a technicality. I could spend now 20 minutes going through this, but it's not very important for us right now. So believe me that if we would work with instead of complex Fourier modes with cosines and sines, then we would get that we will have then these functions would be real, and you will really have a delta between. Every mode will be correlated only with itself. Okay. I will explain qualitatively. Okay. I will explain qualitatively. We're talking about this part or this part? This part is just actually by definition, right? Now for this part, think about what you've done on circulant matrices in the TA session. A circulant matrix is a matrix which has translational symmetry. It's really more like rotational symmetry because we assumed periodic boundary conditions, but it's our model for translational symmetry. And what we found is that the eigenvectors of such a matrix are the Fourier modes. So first, what does this mean? It means that if we take a Fourier transform of our input, the correlation between two different modes will be 0. So we will get only if we take. So just imagine that this was a discretized version of the image. S was a vector and S of k prime was a vector. If we would take two vectors, two projections on different Fourier modes, the average of their product will just be 0 because they're uncorrelated with each other. But if we take a Fourier mode and ask what is its own variance, then it has some variance, which is what you have here. Okay, we will maybe add some discussion on this, but this is not the first time you're learning about Fourier modes, right? The Fourier analysis. Okay. Nevertheless, what this really is telling us is that, again, that different Fourier modes with different k's, up to this issue of the sign, which is a bit confusing but not very confusing. You know what? If I would write it like this, S star of k, then it would be k minus k prime. This is what I told Michael. So vectors with different k's are uncorrelated. This delta function is 0. And the projections on the same k has some variance, which is this g of k. But it turns out, I'm not proving it to you, it turns out that this function is exactly the Fourier transform of this function. Okay, so it's not, they are related to each other in a very strict manner. Okay? Okay, so what I would like to tell you now is something about this function g of k, or this function g of x for natural images. And this is a very remarkable fact, that if you do this exercise and take many images and look at the correlation functions. By the way, if you want to estimate the correlation function, this g of x, one way to do it is in the sense that I wrote here, to average over many images. But because we talked about that, because we have translational symmetry, we can also take one image and estimate this by averaging over many pairs of pixels that all have the same distance between them. It's of course better to do it over many images. So if one does that, one observes very, very robustly the following observation, that if we look at log distance, I will write this as the x axis, and you look at log g of x. So you basically, we're just plotting g of x as a function of x on a log-log scale. If you do this, you find that the data fall very nicely on a straight line over several decades, and the slope of this line is called eta, or minus eta, and this eta is approximately 0.19. This is empirical, but if you do it over many images, you do it again and again, you'll find numbers varying slightly around this. Yes, so this is so it's plus, and the minus I already put in the definition of the slope. What does this mean? It means that g of x has a power law structure. It is proportional to absolute value of x to the minus eta. Which tells you that spatial correlations in images, first of all, have a power law structure, which is very interesting. And the power is quite small, meaning that the correlations decay very slowly as a function of distance. Now, why is it a power law? So there's one very special property of a power law compared to any other function, like an exponential or other functions that you know. And this is that powers of x are what we call scale invariant. Right? If the correlations would decay exponentially, for example, if I would say that g of x would go like exponent of minus x, I would need to put here some scale, something with dimensions of distance, so some x0, in order to characterize, to have a well-defined expression. And this would mean that exponentially decaying correlations have intrinsically a scale in them, right? If they decay like this, then this is a characteristic scale that characterizes the natural images. But if g of x goes like a power law, there is no particular scale that characterizes this dependence. So in a sense, it's invariant if you take one image. If you take an image and you would just zoom in on it or zoom out on it, then up to a prefactor here, you would get the same form of the correlation function. Why would this be true for natural images? Does anybody have a guess? I myself don't know exactly the answer. I mean, this is a topic which is debated, but I think there is really one very strong reason.
What do you mean by natural images?
It's a good question. It's a somewhat vague concept, but any set of images that you really take in the real world displays this structure. So why would it be true that images have no scale in them? No characteristic scale in them.
Maybe it depends on the size of the things in the world.
Okay, so it's a good idea, but let's try to develop it. Why would the size of objects in the world come up in all? Would objects in the world come in all different sizes?
Because it's made up from something.
That is one possibility. Okay, so zooming out and zooming in, one way to do it would be to, to move my lens and the focus of my lens, but I could also move forward or backward, right? Yes, but well, Eliad's idea was good, that the objects might come in, objects come in many different sizes in the world. Yes. Why? But why is that true that they come in different sizes? So one property might be that that there are really objects in every different size. But we know in our natural world we have trees with a size of 10 meters. We don't have trees with the size of a millimeter, and we don't have trees with the size of a kilometer. Right? Exactly. So the point is that images in the natural world can really appear in our visual scene in all possible distances, and therefore their projection on the retina is scaled according to this distance. And I think this is the deep reason, the main reason that that natural images have scale invariance. It's a much more
Is this from many stimuli leveraged?
yeah. But if you would do it if you do it also on one image, on a particular image, then at least for the shorter distance, you can get lots of statistics from summing many different pairs of pixels that have the same distance between them, and you will also observe this statistics. So I think scale invariance has to do with this fact, but to predict this particular power law is a much more interesting mathematical interesting question, both about the world and and the mathematical question. It's not a clear answer. There's no clear answer. There are some theories that try to predict why this is a particular exponent that we measure, but it's still in some sense an open question. But I would like to just mention now that what I told you now is about the statistics of g of x. But as I mentioned to you, g of k is nothing but the Fourier transform of g of x, and therefore, if you take the Fourier transform with a power law, we can say what we will get, and in fact, when you take the Fourier transform with a power law, you also get a power law. So this is just equivalent to the statement that g of k goes like k 1 over k to the power 2. Turns out, if you do the math, that if a function has this power law with this exponent, its Fourier transform will have two-dimensional Fourier transform will have a power law with the exponent minus 2 plus eta, or 1 over 2 minus eta. And you can do the same trick that the same analysis that I discussed here in real space, but from the start do it in Fourier space. So take many natural images, and for each one of them, look at the power spectrum, what we call the power spectrum, the power in different Fourier components, and you will find indeed that it falls very nicely on a log-log plot on a straight line with a slope which is